So what we started out with, we took a Lagrangian with phi 4 interaction but discrete symmetry, okay. And then we got, so we had like okay, let's so let's write it over here, global. So we took the particular case of global U1. Next we took Lagrangian with phi 4 interaction and m squared less than 0, that is very important, and m squared less than 0 with a global U1 continuous symmetry. Okay. So here maybe here I will write a few more things. Phi is equal to phi 1 plus I phi 2 by root 2, and then what happened was that I rewrote it in terms of the physical fields phi 1 tilde and phi 2 tilde, and got m phi 1 tilde is minus 2 m squared and m squared phi 2 tilde is equal to 0, right. So the third one is what I am going to write in some detail. The third one is we took the Lagrangian with local. So in each case, by the way, let me remind you, in each case we got the potential minimum at phi 1 squared plus phi 2 squared, or in the first case only phi squared, it had only one phi, is equal to v squared is equal to minus 6 m squared by lambda, okay, for m squared less than 0 and is equal to 0 for m squared greater than 0. So that we are not going to write at all, we are not interested in that solution, okay. Now I am going to go to local U1 continuous symmetry. So the moment I have local, I define a field. So I have a gauge field. So my total Lagrangian will have the kinetic energy for the scalar field, the potential, which is, should I write it somewhere? Okay, I will write it later, potential for the scalar field, and then we had, so couple this to B mu through minimal coupling. That is the way you do this, right, through minimal coupling. So what is the way to do this? So then the L goes to d mu phi dagger, sorry, d mu phi, and this remains the same, and of course now you have a kinetic energy term for the B field. Now when I analyze this potential, so maybe I should just write this potential, V of phi is equal to m squared phi dagger phi plus lambda by 3 factorial phi dagger phi whole squared. So when I analyze this potential, I get phi 1 squared plus phi 2 squared is equal to, let us call it V squared, is equal to minus 6 m squared by lambda for m squared less than 0. So this does not change at all. I am going to use this solution. So I am going to define phi 1 tilde is phi 1 minus V, phi 2 tilde is phi 2, and then I want to look at the interaction with the gauge field. This is what I stopped at yesterday. So let me do that once more, just to remind you of how it worked. So let me consider d mu phi. So what is d mu? D mu is d mu plus I g b mu. G is some coupling, I don't know what it is. And phi is of course phi 1 plus I phi 2 by root 2. So what will I get? I will get d mu phi 1 plus I d mu phi 2. So there is a 1 by root 2 overall. Okay. Then plus I g. So for phi 1 I will write phi 1 tilde plus v. For phi 2 I will write phi 2 tilde. So let me make this. The v anyway won't matter. So I will get here, there will be two terms, I g v b mu plus I g b mu phi 1 tilde. So that is that term, and then minus g b mu phi 2 tilde. I hope I have got it right. So now if I do d mu phi dagger d mu phi, this will give me half. So this is a plus ib, so I am going to get a squared plus b squared. So this will be d mu phi 1. I am going to drop the tilde because it is painful to write. Everything is a tilde field here. So d mu phi 1 squared plus g squared b mu squared phi 2 tilde squared plus the cross term minus 2 g b mu phi 2 tilde d mu phi 1. Okay, this is the square of this. Now I have to square this, so I will get d mu phi 2 squared plus gv squared b mu squared plus g squared b mu squared phi 1 tilde squared. Then the cross term of this and this, which was our problem term, and then the cross term of this two, g squared v b mu squared phi 1 tilde, and then sorry, so this cross term, and then this cross term. So plus 2 d mu phi 2 into b mu phi 1. Okay, is this clear? I mean, just expanding the brackets. I am more interested in interpreting the terms one by one. So this is where we stopped yesterday, and what did I point out? I pointed out that I have a term here. So this term sits in the Lagrangian, right? So this d mu phi squared sits in the Lagrangian. So L has this term, and therefore this looks like a mass squared for the B field, right? Half m squared b mu squared. So this looks like a nice term. This looks like the kinetic energy for phi 1. This looks like the kinetic energy for phi 2. This is 4 fields interacting, 3 fields interacting, 4 fields interacting, 3 fields interacting, 3 fields interacting. But here is our problem. This is what I stopped at yesterday, that there are only 2 fields here, B and phi 2, and this is not a diagonal piece. These are coupling 2 different fields. So this doesn't contribute to a kinetic energy, doesn't contribute to anything. It's not the mass, it's not anything, it's a problem. So how do we reinterpret such that this nice result that we got, that is we are somehow getting a mass term for the B field, still remains, but this term goes away. For that we have to remind ourselves that what I did was a local U1 invariant. So what does local mean? That the Lagrangian is invariant under a transformation of phi goes to phi prime is equal to e to the I. This is a U1 transformation. So, this is local, let me call it alpha, and I have explicitly put x over here times phi, and we know that simultaneously B mu, that is what the meaning of the local symmetry is, goes to B mu prime, was it minus or plus, minus 1 by G d mu of alpha. This is what we had always, right? This is what a local invariance means. So now let us look at that local invariance, but let us implement it in a very clever fashion. So what they did was write this again. So we had phi was 1 by root 2 phi 1 plus I phi 2, and if you remember this we had written as phi r e to the I phi phase. Okay, so if I expand this for a small phi phase, I think we can put the 1 by root 2 outside, it is not going to bother us. Phi r 1 plus I phi phase. Okay. Now let me write this in. So this will be approximately equal to 1 by root 2 into phi r plus I phi r phi p, and therefore I can identify this as phi 1 and I can identify this as phi 2. Okay. So therefore phi r I can identify as phi 1, which means that I can identify phi tilde. So I can write phi again in terms of the phi tilde fields as 1 by root 2 phi 1 tilde plus v. So I have just written phi r, we had identified as phi 1 times some e to the phi phase I phi phase, and you will see later that if I do this I will get back, maybe I should just do this. So let me expand this again, phi 1 tilde plus v into 1 plus approximately equal to I phi p by v. So this is equal to 1 by root 2. So phi 1 tilde into 1 is phi 1 tilde plus v into 1 is v. Now for the second term, phi 1 tilde into phi p. So phi 1 tilde into phi p, this term, and then I have I phi p. So what I am doing is that, okay, I am dropping terms which are higher order in the fields, just like I stopped with one linear term. So then I get phi 1 plus I phi 2. So now by writing divided by v, I identify phi p itself as phi 2. Is this clear? So now I go back to this. I have now rewritten phi in terms of phi 1 tilde and phi p. Now I make this gauge transformation, and what gauge transformation do I make? I make a very specific gauge transformation. I write phi goes to phi prime is equal to e to the minus I phi p by v into phi. So I have taken alpha to be minus phi p. Is it clear? Which is actually minus, I have identified this to be phi 2, minus phi 2 and phi 2 tilde are the same actually. So phi 2 tilde. Is this clear? It is a very nice trick. So you can see that the phase part of phi, I have simply gauge transformed it away so that phi is, so here let me continue this. So that will be equal to e to the minus I phi 2 tilde by v into e to the plus I phi 2 tilde by v into phi 1 plus v, which is equal to phi 1 plus v. So my phi prime is simply phi 1 tilde plus v, just a trick. Now I go back to this term. So what do I want to do? I want to write d mu phi therefore goes to d mu prime of phi prime. What is d mu prime? D mu was d mu plus Ig b mu. So this will be d mu plus Ig b mu prime. And what is phi prime? It is simply phi 1 tilde plus v, which will be d mu phi 1 tilde, d mu on v is 0 plus I g v b mu prime. I have written the second term first, plus I g b mu prime phi 1 tilde. So you see where we are going now with this, that all those extra terms, so this is d mu prime phi prime squared is simply this mod squared. So again this is a plus ib, so it will be a squared plus b squared. So I will get d mu phi 1 tilde squared. So there is a 1 by root 2 I have forgotten everywhere, sorry, 1 by root 2, please, that 1 by root 2 I have forgotten everywhere. So 1 by root 2, so that will give me a half when I square it, d mu phi 1 squared plus, there are 3 terms because 2 terms I am going to square, gv squared b mu prime squared plus g squared b mu prime squared phi 1 tilde squared plus 2g squared v b prime squared phi 1 tilde. So you see what has happened to phi 2 tilde? Where is phi 2 tilde in this whole thing? No phi 2 tilde. Is it gone? Is it gone? It is sitting here. It is sitting in b mu prime is equal to b mu minus 1 by g d mu of alpha. So now you see that massless field, what was the problem that we had here? We had a gv b mu times d mu phi 2 tilde, right? Now you can see that actually this has gone as one of the redefinition of the b mu field. So you can see that, I hope we can see that, if I take a to be, I mean this gv is always sitting there. So if I take a to be b mu and b to be d mu phi, then I am getting over here, this is a term which is a squared. So a is this whole piece, okay, a. So this is a squared, this is b squared, and this is 2ab. So I have written this as a plus b whole squared, and this a plus b whole squared is simply sitting over here, okay. So I am always allowed to do a Gage transformation. I have always been told that by doing a Gage transformation, my physics is not going to change. Everything will remain the same, right? So I am allowed to do this. The B prime has absorbed this massless Goldstone boson and hence has become massive. Now this is a proper mass term, okay, and we have a kinetic energy term only for the phi 1 field. There is no kinetic energy term for the phi 2 field. It is not a physical field, it is not a propagating field. It simply becomes a component of this massive field. This is a 4-point interaction of b mu with phi. This is a 3-point interaction of b mu with phi, and there are no awkward quadratic terms which cannot be physically interpreted. So you see that this technique, for a local field theory, we have been able to reabsorb this troublesome massless Goldstone mode, and we have got a very nice definition of the mass of this Gage boson. And you see the way we have implemented it is by simply coupling with minimal coupling, and by coupling with minimal coupling you are guaranteed that the Lagrangian is invariant under the local transformation. So if I had written a term which contains L is equal to half mb squared b mu, if I had written an explicit mass term in the Lagrangian, this would not have been invariant under the U1 local transformation, because B would have gone to B prime and therefore there are extra pieces. You would not have got a, an invariant Lagrangian. But by introducing the coupling in this very complex way, by interacting with this scalar field phi, you have got a massive particle and retained the symmetry of this Lagrangian. Is it clear? Is it clear? And you have still got your phi 1 tilde. I did not show you that part. There is a potential term V of phi minus V of phi, and that still will contain the mass term for the phi 1, and it has no other terms which contain it has no terms which couple to the B field, so there will be no trouble coming from the V of phi. So that means now we have two massive, so we started out with massless gauge boson and peculiar charged phi which had negative mass squared for both its degrees of freedom. We ended up with one massive scalar, so we have one massive scalar m phi 1 tilde is minus 2m squared, so let us call this capital M, and we have m b squared is equal to gv squared. So we have ended up with two massive particles. We had one massless vector boson with 2 degrees of freedom and this scalar with 2 degrees of freedom. Now I have a massive gauge boson with 3 degrees of freedom and one massive scalar, so I still have 4 degrees of freedom. Is it clear? Shall I proceed to do the SU2 cross U1 case?
Yeah, so can you?
Yeah, ask.
So I have a question.
Yeah.
So can you please repeat? You said something that the symmetry is still retained. What? There's no gauge symmetry. U1 gauge symmetry is broken, right?
No, where is the U1 gauge symmetry broken? U1 gauge symmetry is not broken, right? U1 gauge symmetry, see, this is the whole point. Maybe I should have said it in those points 1, 2, 3. What we are saying is that the Lagrangian still respects the symmetry. The ground state does not. Okay. So the ground state, because I have specified phi 1 is phi 1 tilde plus V and phi 2 is phi 2 tilde, I have pulled out one point of the infinitely many possible ground state solutions, because I want my ground state to be unique. So my ground state does not respect the U1 symmetry, but the Lagrangian still does, because I could have rewritten the Lagrangian in terms of phi 1 tilde and phi 2 tilde, but I can equally well write it in terms of phi 1 and phi 2. If I write it in terms of phi 1, phi 2 and B, then this Lagrangian is completely invariant under local gauge transformation, right? So if I rewrite it in terms of phi 1 tilde, phi 2 tilde and B prime, it is still invariant under local gauge transformation. So the Lagrangian retains that symmetry. That is why it is called spontaneous symmetry breaking. If I had put an explicit mass term, this is called explicit symmetry breaking. But it is because of the nature of the ground state and the way we have written this m squared less than 0 and picked out one solution out of the infinitely many, that is why the continuous symmetry is required, that we get a spontaneous symmetry breaking and the ground state does not respect. So the ground state breaks U1, but the Lagrangian is still invariant under the local transformation. This is a very important point to remember. And therefore, this mass term, if I had put this mass term, and I could have got rid of all this Higgs mechanism and all this complication, but then I would have explicitly broken this U1 and then of course later the SU2 symmetry, but I am not doing it that way. I am doing it in a way that will preserve that invariance. Okay. So if you have understood this trick, I am not going to repeat that trick. Sorry, yeah, ask the question. Yes.
Yeah. So that part is clear, but I have still one more doubt.
Yeah.
And it seems to me that in the ground state there's no U1 gauge symmetry. Yeah, but so it's as if we have broken the gauge symmetry and then we have used the gauge symmetry to absorb the phi 2 part, because we define.
It is a redefinition. Yes, it is a redefinition. Yes.
What exactly?
So if you want, the way people usually say it very descriptively is that the massless gauge field eats up the Goldstone boson and becomes massive. That is the way to understand. It's a very crude but very effective description, okay. So it absorbs or takes away the degree of freedom and itself becomes massive. See, you must understand one thing about this. We can ask many questions. How does the mass squared become negative? Why is it negative? Was it always negative? The way I would like to think of it, because there are many people who have tried to understand this Higgs mechanism through something called dynamical symmetry breaking. So let's think of, the universe started as a big bang, right? Universe started as a big bang. At that time, there were no particles, right? I mean, the particles were produced some little time later, and then you had electrons, and then you had the protons, so all the quarks come into existence and so on. So the Higgs field has to have been existing from the beginning, because if it doesn't exist from the beginning, there will be no masses for these particles. But you can think of it as something like, maybe I should take this off. The way people try to physically understand it is that you are at a very high energy scale. See, the Big Bang is at a very, very high energy scale. Then as the universe cools, you're coming down in the energy scale. Okay. So somewhere there is some interaction and we don't know. See, we only know standard model as a low energy theory. We do not know that standard model is the correct theory all the way up to Planck scale, where gravity is also a part of this. See, gravity doesn't come in here because we don't have a theory of gravity. We will find that even if you try to write a tree level diagram of gravity, it diverges. So gravity cannot be unified along with the electroweak and strong interactions. So, but we know that at some point, whole formation of universe is due to gravity, right? So gravity has to be incorporated at some point. So somewhere at this high energy scales, okay, maybe you had something where m squared was greater than 0, but as the universe is evolving down in energy, some interaction, some new interaction that we still don't know about, actually does something and flips m squared to less than 0. Immediately after that, spontaneous symmetry happens, breaking happens, and you get a standard model which is a low energy sector. This is one way of looking at it, okay, we don't know. People have tried to write many models, people have tried to write composite Higgs models, people have tried to do many things to get around the fact that this is such a weird and like completely opaque way of getting the masses, but none have been successful till now, okay. So you can think that Higgs was actually a bound state of some other set of particles, and only at low energies it appears to us the way it does. So anything, anything that you can think of, I mean, there are like not hundreds but thousands of papers written in this area. So there are many, many models. At this level, all I can say is that yes, there is some very peculiar mechanism. So whether this m squared was always 0 from the beginning of time, whether it became less than 0 because of interaction, whatever it may be, at some scale, spontaneous symmetry breaking happens and you get the standard model with the broken symmetry. So maybe it is possible that at a very high energy this symmetry is restored, which means that at a very high energy scale all particles are massless, because once the symmetry is restored, then you have m squared greater than 0, which means that you are not having your special ground state which had that non-trivial vacuum expectation value, which means that everything else follows as phi 1 is 0, phi 2 is 0, you cannot couple it to the any sector and give masses, nothing happens, okay, which means that at some very high energy scale all these particles are massless, which seems kind of reasonable. We still don't know how it can be implemented, what are the other interactions can be there, but that's one way of looking at it, okay. So what you have is here, somehow standard model is a low energy theory. At that low energy scale, already something has happened to make m squared negative for this scalar field, and that drives the entire spontaneous symmetry breaking. So you see the particles with masses. So all around us, our particles have mass, and we also have mass, and that is our universe. Is it okay? Okay. As I said, I don't have a satisfactory explanation, but the only thing we can do is say a lot of words. But it has troubled many people, and many people are still thinking about it. And the amazing thing is that you will see now when I write the standard model and the Higgs mechanism, you will see that with the minimum number of parameters, this whole thing works so beautifully. And therefore, even before the discovery of the Higgs, as I said, people were convinced that this is the way to do things, okay. This is one place where theory was being taught. I mean, I myself, I think taught, I taught standard model for at least 15 years before the discovery of the Higgs. Okay, and I never had any doubts that this is actually the correct theory. Okay, even though it is so strange. So now we will go to standard model. So what we will do is, let us look at the electroweak theory. So we will go back to our SU2L cross U1Y and try to give the appropriate masses through this Higgs mechanism, Higgs Kibble or spontaneous symmetry breaking mechanism, whatever it may be called. So you can see that what is it that we require? We have W plus, W minus, Z and A, which are actually coming from WA of SU2L and B of U1. Of this, the A field must remain massless, and these three must acquire a mass, and W plus and W minus must acquire the same mass. So the simplest way to do this is to have what is called a Higgs or a scalar doublet. So Higgs scalar isospin doublet. So what are we introducing here? I am going to introduce now an isospin doublet phi, which will be the scalar field, which has our famous 1 by root 2. This is just a normalization factor. Phi 3 plus I phi 4, phi 1 plus I phi 2. Now if you just look at U and D, okay, or neutrino and electron, you can see that delta Q is equal to 1, whichever way. So let me write it as Q upper minus Q lower is equal to 1. Okay, so we will consider this to have Q is equal to 1, Q is equal to 0. This is required for the SU2 part of things, right? You have to couple sigma plus sigma minus to W plus W minus. Now why have I written this like this? Because I want to give vacuum expectation value to phi 1. So far we have always been talking about phi 1 as acquiring the non-zero vacuum expectation value, okay, and this will become the massive Goldstone, this will become the massive Higgs boson, and that is therefore neutral, okay, and Q2, Q3, Q4, so these are the remaining objects which will become massless Goldstone bosons, and when you couple them to these objects, there are exactly 3 fields which will give masses to the 3 particles and leave the A field massless. So how are we going to do this coupling? To understand how to give masses, what did we do when we tried to get mass for the U1 Gage boson? We looked at the term d mu phi, right? So now we have to look at the term d mu phi again. So just for to remind you, we had L was L fermion had okay, let me write them down once more. Let us not go in a hurry. Let me write it down here. So the Lagrangian now has many parts. So it will have psi bar. So let me write one. I'll write one I gamma mu. So d mu L mu E L plus ER bar I gamma mu d mu R ER plus, I am writing only one generation, only the leptons, but you remember this, right? And what was d mu L? Was d mu, and d mu L saw both the left-handed SU2 and the U1. So it was Ig sigma A by 2 W mu A plus the G prime coupling for the U1 hypercharge by 2 d mu. And what was d mu r? D mu plus Ig prime y r by 2 d mu. Right? Now what are we looking at? We want to look at how the field couples to phi. So we have to write d mu phi. So I'm going to couple this to plus. So d mu phi squared minus v of phi minus kinetic energy terms, etc. I'm not going to write all that. Okay, all that will remain. So this will contain the kinetic energy terms of the U1 fields, SU2 fields, everything. So minus half trace G mu nu A, G mu nu, all those things which I don't care about. Okay, I am only interested in looking at d mu phi. So how do these gauge fields couple to the Higgs field? So what is the d mu phi? D mu was d mu plus I G sigma A by 2 W mu A plus I G prime y of the Higgs by 2 B mu. And phi was this whole thing. Okay. Now I am not interested in asking what is the interaction of the phi fields with the W and the B. I am only interested in how does the interaction with the phi field give you the mass for the appropriate W and Z. So I am really interested in only looking at this portion. What is the portion I am interested in? 0 V plus 1 by root 2 dynamical fields. So what happens with the dynamical field? The phi 1 field becomes massive because of the V of phi. The phi 2, phi 3, phi 4 will all have to be absorbed by Gage transformation into these W primes and B primes. I am not going to do any of that. I am going to assume it all can be done and just simplify the problem to look at only this portion. Because we know that this is what gives the mass to these gauge bosons, right? So now I will have to write it again, except before I continue, let us ask what is the hypercharge of this field. So we have written Q is equal to 1, so let us write Q is equal to I3 plus Y by 2. Okay, we know that because it is in a doublet, the hypercharge should be the same for both the members of the doublet. We will just check it here. So 1 is equal to half plus Y by 2. Right? So 1 minus half is y by 2, y is equal to 1. Similarly, 0 is equal to minus half plus y by 2, again y is equal to 1. So y phi is equal to 1. Is this clear? So I will now write this is 1 by root 2. Now I am going to drop d mu also because that is going to give me kinetic energy terms. I am only looking for the interaction. So I will write it as I by 2. I by 2 root 2 because everything has a 2. Now I will write this as, if you remember what was sigma A W A, I will just write it in the corner. Sigma A W A was sigma plus W plus, which gave you a root 2 W plus here, root 2 W plus here, and the W3 was 1 0 0 minus 1, right? I hope you remember this. Should I rederive this or do you remember this? I wrote sigma A WA as, huh? You don't remember it? Okay, fine. Then let me just pause it here and write it correct neatly on the other side. So I'm going to take this off. So sigma A WA is sigma 1 W1 plus sigma 2 W2 plus sigma 3 W3, which can be written like this. I'll explain what each one is. So sigma 3 W3 are the same. Sigma plus minus are sigma 1 plus minus I sigma 2 by root 2, and W plus W minus are W1 minus I W2 by root 2. So let us look at only these two terms. So sigma plus W plus sigma minus W minus is equal to sigma 1 plus psi sigma 2 into W1 minus psi. By the way, every W1 is W1 mu. I hope you know that. Plus sigma minus W minus, and there is a 1 by 2 from the 1 by root 2 1 by root 2. So you can see it is sigma 1 W1 plus sigma 1 W1 by 2 is sigma 1 W1 minus sigma 1 W2 and plus I sigma 1 W2 will cancel. Then plus I sigma 2 W1 and minus I sigma 2 W1 will cancel. Plus into minus I is 1. So sigma 2 W2 plus sigma 2 W2 by 2 is plus sigma 2 W2. So this is nothing but sigma 2 W2 plus sigma 1 W1. Okay. So I can write it like this. Now what is sigma plus? It is the raising operator. So sigma, let me write it over here. Sigma plus is 0 root 2 0 0. This is trivial, you can just please multiply this and check. Sigma minus is 0 root 2 lowering operator, and sigma 3 is 1 0 0 minus 1. So when I do sigma plus into W plus, I get root 2 W plus. So let me write it here. So this will be I have already taken out, by 2 I have taken out. So my matrix element will contain G times root 2 W plus root 2 sigma plus into W plus, root 2 W plus in the top right hand corner. It will contain root 2 G W minus in the bottom right left hand corner, G root 2 W minus in this corner. Sigma 3 will go with W3, so this will be W3 minus W3. So I have put a G because the G is here, minus GW3. Okay, and now that is done with the sigma W. Now I have Wi-Fi is equal to 1, so this is I which I have taken out. So G prime is left, by 2 I have taken out, so G prime B, and this is multiplied by unit matrix, right. So this will be plus G prime B plus G prime B into 0 B. Okay, which is I by 2 root 2. I am going to do the multiplication. So this into this is 0. So this will give me G root 2, let me call it root 2 G W plus, and the second term is this into 0 and this into V. So I get minus G, so let me pull the minus outside, GW3 minus G prime B V. Okay, up till here? So what I want to do is, I want to find d mu phi dagger, d mu phi, right? So that I and minus I will go away. So I will get 1 by 2 2s are 4 into 2 is 8. Then the transpose of this, they are all real, right? So root 2 G W. So I have to do d mu phi dagger, right? So dagger of W plus is W minus, then the minus G W3 minus G prime B into root 2 G W plus into the vector, right, minus G W3 minus G prime B. This is d mu phi dagger, this is d mu phi. So what is that? So root 2 into 2 is 2, G squared W plus W minus. I have dropped something very clearly. I have dropped the V over here. This into this plus this into V. So there is a V over here. V over here and a V over here. Because I know that I have to get GV as the answer, right? W plus W minus. So this into this plus this into this. So minus into minus will give you plus GW3 minus G prime B squared. Again there was a V over here and a V over here, V over here and a V over here, V squared. So we have now terms which look like the mass terms, except that we have to convert the W3 and B into A and Z. Do you remember? We rewrote W3 and B in A and Z. So first of all, let's get rid of the charged case. So here you have G squared V squared by 4 W plus W minus. You remember W plus was W1 plus minus I W2 by root 2, and this was W1 plus I W2 by root 2. So you can see that this is actually G squared V squared by 4 W1 squared plus W2 squared by 2. Just multiply A plus IB into A minus IB, you will get this, okay. So which means that the mass of W1 squared is equal to the mass of the W2 squared is equal to, because half m squared W squared, right, is equal to G squared V squared by 4. So we have now got the mass of the W plus W minus bosons to be GV by 2. Now G is already known. G is known from what? G is known because you remember G sin theta is equal to E, or you can write G in terms of GF, the Fermi constant. So question is V known? So either you must know theta W or you must know the mass of the Higgs, and I will put in numbers once I have completed this part of the calculation. So what should I get from the second term? From the second term I should get that the photon is massless and the Z boson is massive. So you remember now, let us look at, so consider G W3 minus G prime B square. You remember G is G sin theta W was G prime cos theta W. We did this is equal to E. We did this when we got the interactions in terms of W and Z, right. So we have is equal to V squared G squared. So let me first put them in. G W3. So G prime is G tan theta W, which is square. So tan theta W is sin by cos. So I am now going to take out G squared cos squared theta W. So G has been taken out as G squared, cos theta W has been taken out as cos squared theta W. So there is a cos theta W here. So I have cos theta W W3 mu minus sin theta W B mu squared. Does anybody remember what this is? You remember we had defined Z mu is equal to W3 cos theta W minus sin theta W B mu, and A mu is equal to is equal to sin theta W W3 plus cos theta W B mu. This is how we had re-expressed Z and A in terms of the Weinberg mixing angle. If you want, go back to the old notes and check this. So what is this? This is exactly, so V squared. So there is an overall 1 by 8. So might as well put everything back together. So nice, right? So what you have got is that the mass of the W is GV by 2, mass of the, so this I can write as half. So mass of the Z is V squared G squared by 4 cos squared theta W, and mass of the photon is exactly as required, 0. Okay? Is this clear? Is this so with very minimal, just one Higgs doublet, we are able to give masses, so that W plus W minus have the same mass, which is different from the mass of the Z, and you can see that mW squared by mz squared is equal to, so this is G squared V squared by 4 will cancel, is just cos squared theta W is, this is called the rho parameter. You can show that if you introduce Higgs as a doublet, you will get rho is equal to 1. If you introduce Higgs as a triplet, you will not get rho equal to 1. And experimentally, this means that mw squared is less than mz squared, because cos squared theta w is always less than 1. So you have many choices now. You can experimentally find out what is mw and mz and find cos square theta w, or you can go back to this equation and find, where is that here? You can go back to the old couplings. You remember from g sine theta, where is that here? From here you can ask, you can find g from, you remember gf by root 2 was g squared by 8 mw squared. So you know gf, if you know only mw, you know g, so from g you know e, and therefore you can find sin theta w. Then you have a prediction for mz, because once you know sin theta w and mw, you have a prediction for mz, and they are all exactly consistent. So as I said, we have mw is 80 GeV, mz is 91 GeV. It gives you sin squared theta w, approximately a 0.23 or something like that, I don't know. And you can also check it with this. So you can also check by putting in, so square this, write E squared as 4 pi alpha. You know alpha is the fine structure constant. So there are many ways in which to trade off one parameter against the other. And finally you come back to the fact that the absolute value of mw squared is g squared v squared by 4. And from here you will get v squared is of the order of 250 GeV squared. Okay, so your vacuum expectation value V of the phi 1 field can be predicted by knowing the other. So you know the mass of this, you know G because you know E and sin theta W, for example, and therefore you will get V squared. You can even put in the numbers and check. Okay, so you can even put, okay, so you have, maybe let us do some numbers. Let us do some numbers so that we will get a feel for things. So let us write G squared is equal to 8 mw squared gf by root 2. I am not going to worry about root 2, okay. So let's call 8 as 10. So mw is 80 squared, gf is 10 power minus 5. So this is 6, so this is about 10 power 4, or yeah, and there's another 8 outside, right. So this is about 10 power 4 into 10 power minus 5. Let's do it correctly. 8 into 6064 into 10 power minus 3. That is 500, so around 0.5. 0.5. So mw is equal to gv by 2. So v is equal to 2 mw by g, that is about 4 mw. So 8 4s are 32. Okay. So I mean I am just doing round numbers here. So basically you get the order of magnitude. Once you get this, you can ask the last question. You know that the mass of the Higgs which is left over is minus 2 m squared, right, and that is we know that V squared is equal to minus 6 m squared by lambda. So mh squared is minus m square is V squared by 3 lambda. So we don't know what that is. So that is some 250 squared by 3 lambda. Now for perturbation theory to hold, lambda must be less than 1, right? So this gives you an upper bound on the mass of the Higgs. You can get mass of the Higgs is less than approximately 1 TeV. 1000 comes out to be about 1000 GeV, right? Roughly about few hundred, I think it comes out to be about 700 GeV or something like that. So everybody knew that if you don't find the Higgs within 1 TeV, then your standard model is going to have a problem. Either your scalar sector is not amenable to perturbative calculations, or you are not going to find the Higgs at all and this mechanism does not work. So people had been searching, that is why the search area was all the way up to 1000 GeV, which is 1 TeV, and now we know that the Higgs mass is, we know that mh is 125 GeV. So you can put all this back and find that lambda is very much less than 1, is less than 1 but not that much less than 1. So there is already problems now. So lambda is quite close to 1, and maybe I will make remarks on this in the last class because I have not talked to you about running coupling constants, okay. So I will talk about this triviality bounds and lambda value from this values of mh and v and so on like that, and some important issues are there to be discovered, okay. But now you can see that everything comes out nicely. You have mw has to be less than mz, at most it can be equal because of this factor, and it comes out right, okay. And the test for many theories beyond the standard model is that the observed rho is very much close to 1, okay. It's 1 point naught something plus minus some error bar. So any theory that you want to write to extend the standard model must respect this observation. It's a very important observation, okay. And you can see that, okay, now I make some formal remarks before I stop. So let us see what we have done, okay. We have taken, in fact I want to leave this thing, so we have taken a local, that means I have invariance in general. So L is invariant, so let me write L is invariant under this local SU2 cross U1y, okay. What is a particular gauge? Let us consider any particular gauge transformation. So I have phi, I am not worried about the psi fields are doing fine. I have phi goes to phi prime is equal to e to the I sigma a theta a by 2 phi. Let me not worry about the u1 part will be fine, okay. So let us consider the gauge transformation on the ground state. So phi is equal to 1 by root 2 0 v. So if I expand this, this will be 1 plus sigma a theta a by 2 acting on this. So essentially I am interested in sigma a acting on phi. Now you can please do this, maybe we can do this quickly. Let us take sigma 3 acting on phi or sigma 1 acting on phi. So 0, 1, 1, 0. I am going to drop the 1 by root 2, okay. Is 0 into 0 plus 1 into v, 1 into 0, okay. So it is not leaving this thing invariant, right. Similarly you can put sigma 2, similarly you can put sigma 3, and therefore you can see that this ground state is not invariant under this transformation. This is exactly what we mean by spontaneous symmetry breaking, okay. That even though the Lagrangian, we have not tampered with the original Lagrangian, even though the Lagrangian is invariant under SU2 cross U1, And in fact, we have made sure even the coupling to the scalar fields is through the covariant derivative. So we have not tampered with that sector at all, but the ground state is not invariant under that transformation. And so that brings us to the final remark. If I have, let us take only SU2. So if I have in general, if Lagrangian is invariant under some n symmetries and n are broken by the ground. One moment. Ground state, then there will be so total number of symmetries minus the broken ones, massive bosons and in massless ones. Okay. So here you can see that these are the generators of SU2. Each one of them is broken. So SU2L is completely broken, not at the Lagrangian level. When I say broken, I mean by the ground state, completely broken, and only the remaining symmetry that is there is actually the U1 electromagnetic. So what you will have is that SU2L cross U1Y breaks through spontaneous symmetry breaking to U1 electromagnetic, or you can call it U1Q, and that is why you have the combination. So isospin is broken. This is not a good quantum number, this is not a good quantum number, but the charge is a good quantum number. And we know that ultimately what happens is that the photon is massless, nothing is broken in that sector, and your electromagnetism remains completely clean, except that this electromagnetism U1 is not the same as this U1. This is the U1 of hypercharge. All this gets broken to leave you with one residual U1 symmetry for the ground state, and that is this charge invariance. Is it okay? So this is the way in which, by coupling the phi to your gauge fields, you have got masses exactly as required for W plus W minus and Z and not for A. So the final thing is the weakest part of the standard model, but also has been tested very nicely now at LHC, is how to give masses to the fermions. So far we had fermions and gauge bosons massless. We have now given masses to the gauge bosons, and in the last and final step we will give masses to the electrons and quarks. Okay, so I will stop here. This completes, the next class will complete the whole issue of spontaneous symmetry breaking. Maybe I will make a few remarks about the final Lagrangian and quark mixing and so on. We will talk about that in one class later. So that means next Tuesday I will be more or less done with the main content. As I said, I wanted one lecture extra to make general remarks. After that you can start making your presentations. Okay? Is it okay?
Ma'am, when do we have to submit the write-up?
This weekend.
Like, is it fine like if I submit on Monday or Tuesday?
Yeah, it's okay.
Okay.
Just don't spend too long over it, okay? Because
Yes, ma'am, actually
yeah.
I need the weekend, Saturday.
Yeah, you use the weekend, yeah, but then one more assignment will come up. So don't spend too much time on that. This whole week you should have spent on this. So you use the weekend if you wish, but I will be giving you one assignment, but that will probably cover things about this couplings and spontaneous symmetry breaking.
The presentation is going to be held on next week or the coming week?
The coming week.
You said you will be teaching us on Tuesday.
Yeah, so Tuesday I will take class. So Thursday you can start presenting.
From Thursday. Okay.
Yeah, from Thursday, and as I said, I would like one more class sometime. We will find out either next week or the week after, so that we have some time to, make the presentations as well. Okay. I will send you a mail around. What do you have any classes at all in the afternoon?
Not on Tuesday and Thursday.
Okay.
Not on Tuesday and Thursday.
Oh, but other days you do have class in the afternoon, is it? I see.
2 to 3:30 we have QFT low energy.
Oh, I see. Okay.
Hello?
Yeah, I heard. Okay. I see. That is on Monday, Wednesday, Friday, is it?
Yes, ma'am.
Okay. Okay, let me see. Let's see how we can do this. Maybe I will send mail around and ask you for inputs. Okay. So one class either on then Monday, Wednesday, Friday mornings, or maybe even later than the QFT classes. Let's see. We can discuss it offline. Oh, you have 9:30 to 1 plus afternoon lecture, is it?
Yeah, some people have that. The afternoon lecture is, I think, only Koina and K.
Yeah, but I mean they are there, right? I mean they also
And
need to.
Jatino.
Yeah, okay, fine. No. We don't want to overlap any other course. That's for sure. So we will try to find a non-overlapping time. We will take it offline. We will do it on email.
Ma'am, this coursework will end on 18th, right? So we
Yeah.
already have 1 day.
Yeah, so that's what. Let me calculate all this and then get back to you. Okay. I don't know about.
3 days for presentation and then 1 day. We have 4 more classes.
Yeah, 4 more classes. Yeah, so let me just look up the calendar and let you know. What about the final exam? I think you guys should finish it off. It's anyway going to be a take home. I can give it to you on 17th or 18th. You can give it to me on 19th or 20th. Or I can give it to you on 15th and you can give it back to me on 18th. Because these presentations are not going to be part of your exam material, right? Exam material I will finish tomorrow, I mean on Tuesday. So,
Ma'am, is the take-home exam going to be for like 2 or 3 days, as you say?
yeah. I never give you more than a exam which will take 2 to 3 hours to solve. But you can spend 2-3 days on it, exactly like you spent for this thing. But please, don't get stuck. You ask for input, okay? Ask for help and learn something and get something out of this course. See, the whole idea of this course is to tell you what particle physics is about, what are the kinds of things that we study here, and this is just a very basic introduction to the whole area. So I want you to go away feeling that you have learned something, okay? I don't want you to feel that, this is beyond you to understand or you're never going to look at it again, right?
The exam should be after assignments, right?
Yeah, but you can choose. That's why I don't want to push the assignment too far. So if I give you the assignment in the next week and then you have the week after that to do the exam in, right? But anyway, it's all open notes. You don't have to memorize anything. You have to just be aware of what is happening.
Told that we have to apply for the exams after we go there.
See, the thing is,
Information from the academic coordinator.
see, it can be, but even if you come here, I'm going to give you a take-home exam. It makes no difference to me, except that if we wait and I have no idea when you're going to come. So if we wait until you come here and then you are going to forget all the stuff, and whether you're going to be writing exams or doing the next semester material, I would prefer to finish it off. That's see.
So if we have exams around 18 or in December itself, then we won't have again on January or something.
No. Why should I give you again?
Then it's fine for me if we win again.
Yeah, but I want a consensus from all of you. That's why I keep telling you these things.
I'm also fine with
Can we have the exams after 18?
Yeah, that's also fine with me. It's just that if you guys want to take off for vacation, I don't know, there's nowhere to go. But if you want to take off,
It's very normal to forget many of the stuff.
I think so, yeah. And this is the kind of thing. See, you can see, what particle physics requires is to be familiar with lot of computation. Okay, a lot of this stuff gets done nowadays on computers. You don't really calculate traces by hand. You don't integrate by hand. All this is done, through numerical. Very little of it is actually done analytically. Okay, that's a different challenge. You can also do a lot of basic field theory stuff which is done analytically. So this is really so that once you've learned all this stuff and you've learned all these techniques, write the exam and be done with it. Otherwise, again, you'll have to go back and look at those notes and make sense of it. It's going to be, in one of these few things. 2 questions I'll call assignment, 2 questions I'll call final exam. That's all. Okay. In the final exam, I will not trouble you with another trace calculation.
And so basically, like by the end of next week, we'll be sending the assignment. And then until 18th, we have to submit the assignment.
In fact, I can do one thing. I can give you the assignment right away. You can take your time to finish the assignment while you're preparing for your presentations, so that I'm not holding you up. Those who are prepared can go ahead and solve the assignment, but I'll give enough time for everybody to hand the assignment so that you don't have to worry about it. So in fact, I'll give you the assignment today or tomorrow. Okay. Okay.
When did you say the deadline for the assignment?
Oh, sorry, just one at a time. Deadline for the assignment is couple of days after you finished all your presentations.
Okay.
So that the person who finishes the presentation last. Yeah, that's fine with me also. It's fine. I mean, yeah. Yeah, that's okay.
It
That's
is good to have in December itself. Like I'm not preferring on January.
yeah, I think so. I mean, I would hate it. Okay, if you ask me to write an exam 3 weeks after being taught it, I don't want to. And as I said, anyway, even if you come here, only thing is that you can ask me physically. You can, say, ma'am, look at my answer sheet and correct the factor of 2 that I can't find. I mean, that's the only difference, okay? But if you want, you can scan your answer sheet, send it to me and say, I'm stuck here. I will send you back whatever help I can send, okay? That is not a... See, I am not interested in your factors of 2, and you can see even my teaching, I am not interested in factors of 2 and pi and the concepts. You must understand conceptually what is happening. You must understand if someone tells you what are the main aspects of a standard model, how is it that particles have certain properties and what are the interactions based on these properties. I think you should be able to, for 15 minutes, you should be able to give a lecture on it based on the content of this course. That's really what I'm aiming for. Okay. And then, of course, you have all your life to study. I mean, I'm assuming that all of you are going to stay in physics forever, right? And some of you will be interested in this area, some of you are not interested in this area, but there's a certain, minimum kind of communication that I was hoping for in this course. As I said, this long distance online teaching is really a challenge. It's very boring to teach particle physics when I am doing all the calculations and you're simply watching from so far away. But anyway, to the extent that I could do, I have done. So I still feel that, this kind of working out so many numerical steps and, calculations, best is to finish it off when I have just taught you the stuff. Okay. So yeah. See, I am completely willing to send you even the question paper for the final exam and say that you return it on 21st or 22nd or whatever. I mean, see, you can cheat, okay? Everyone can cheat. There's always room for cheating. But you are all adults. You are mature enough to say that I want to study the subject. I want to learn physics. Then nothing is gained by just copying from somewhere. And think through, discuss with each other, write your own answer. It's always, for me, that's the main thing, okay? Marks and all that, I mean, if you have not got anything out of the course, then I think I would be really sad. But even that, I mean, life goes on, it cannot be helped, okay? But as I said, use every interaction opportunity as a way to learn something more. So for me, exam is also that. Use it as a way to just learn something more. You can discuss with others, discuss with me, but then once you start calculating on your own, you will find that it works out all fine. Then you get the hang of things, and that is something that for theoretical physicists is a very important thing. So whether it's particle physics, condensed matter, optics, anything, this ability to look at patterns, to see things, to be able to work out. For example, you can write all these sigma plus, sigma minus, but to be able to do it in compact way, to have a solution in half a page and not 5 pages. These are the important things that you have to train yourself to do to be a good theorist. Because the math must not get you down. You should be able to see the physics through the math, okay? And for that, it's just a matter of doing again and again until those patterns become familiar. And that's why I keep telling you, people should just keep working. I mean, so I didn't know all this when I was born, right? It's just that after doing it for like decades, it's just there. So whether root 2 is there or not, the fact that the raising operator has to have an entry in the top right hand corner makes sense. Only then it can raise, right? So that's how you should remember these things. Even if you put 1 there instead of root 2, I will still accept the answer. Those factors, some textbook will tell you what it is. Is it okay? So I will send the assignments today or tomorrow itself. I have to write an assignment. and then you people can practice for your presentation. And by this weekend or by Monday latest, you please send the write-up in. Okay? Fine. Shall we stop here?